Well, thanks very much. And actually, it's a very interesting audience being EurIPS. So there's probably a little bit less need to sort of explain and demystify AI. This is probably one of the more expert AI audiences that I usually speak to. So I hope the things I say make sense. I've got today, I'm going to start my timer. So I thought I'd give an overview of AI for nature. I've visited Denmark the first time a long time ago, I think 23 years ago. And I think, I haven't checked this, but I remember that you call it a s'moresbrod, the thing we all call a smorgasbord. Is that correct? Is it actually called a s'moresbrod? But anyway, so I guess this is a s'moresbrod or a smorgasbord of ideas around AI for nature, I think. So I'll try and get through that and not go too deep on any one thing. So very quickly then, in terms of the challenge, there's an increasing recognition that biodiversity is key to global sustainability and the global economy. For example, this list on the left here this is from the World Economic Forum, and this is their most recent assessment of risks to the global economy. They look at all sources of risk to the global economy for the next 10 years, and they put biodiversity second, just under extreme weather. And in response to this and many other sources of evidence, the good news is that we're seeing biodiversity become a major focus for emerging policy and action in key sectors. So that's the governmental sector, but increasingly the private sector as well, like the finance sector, the manufacturing sector. And we're seeing emerging policies like 30 by 30. This is 189 countries have signed up to protect 30% of land and sea by the year 2030. Look at the joint statement coming out of COP28 on climate, nature and people, thinking of that as a joint. We need to think of that as a joint problem and not just focus on climate or not just focus on one part alone. But action in this area is often blocked by information gaps. For example, we don't know where the habitats are, we don't know where the species are, we don't know where the key threats are and so on. But strangely, at the same time as we have information gaps, we can often be blocked by decision complexity. So when we actually go to take any actual decision, it turns out that we have lots and lots of factors to consider on the one hand, and on the other hand, we've got some big information gaps. And that really is sort of the challenge here is, can we use AI then to address the information gaps and the information complexity to help unlock all of this kind of goodwill globally to help solve the biodiversity crisis? So that's a kind of very serious way of putting it. But I wanted to make sure I got this in, and I couldn't think of any way to illustrate excitement and joy other than the words excitement and joy. I just want to hopefully you feel this. I just want to get across is, yes, it's important to do this, but it's also like really exciting to work on these problems because the science of ecology, which is probably the oldest science, right? Traces right back to our earliest roots as hunter-gatherers and so on, is going through an inflection point right now with the emergence of incredible new tools, themselves, of course, building off the developments in open big data sets and compute and so on. And there's just so many opportunities to apply AI in this area in a way that is transformative in that science, and that the field is like very, very keen to receive this kind of innovation. And I think there's also an inherent joy in working with nature. I think there's something about working with plants and animals, even if you're working with a spreadsheet, just with numbers, just the knowledge that those numbers are somehow connected to plants and animals, just it's more of a joyful spreadsheet than other spreadsheets, I think. And also the people in this area, and I know people generally in the world of machine learning, they are nice, but honestly, nature people are really nice. Like and also very diverse. Like we care about biodiversity and human diversity. So I think we genuinely are quite a diverse and group, an inclusive community that actually values diversity as well. So I think there's a lot of excitement and joy in this. And I hope that comes across today because it's deadly serious stuff, this biodiversity crisis, but it's also exciting and joyful. Okay, right, back to the serious bit though. So this is the overview I wanted to give. And each time I give this is a framework that we've been using for a while to think about how we might apply AI to the biodiversity crisis. And each time I give this overview, I'm a little bit nervous because it seems kind of simple in some ways. But one of the reasons I like to do it is I think it helps to remind us and makes us reflect on where we're investing and where we're not investing and different ways that we could apply AI. So the idea here is that ultimately what matters is what people do, those actors taking decisions and acting, whether that's a government deciding where to protect or whether it's a smallholder farmer looking to do regenerative agriculture decisions. And the idea is, well, so how can AI feed into that? And again, address these information gaps and decision complexity. And there are at least 4 different sort of categories, I think, where we could apply AI as represented by this sort of deep learning symbol. So one of those is AI-assisted data. I'll come to this, but it's the idea of pulling in data from the field, but also mining historical data sets. AI-assisted mapping, that's aggregating those data together with other sources of data to basically fill the gaps, especially and when those gaps are geospatial, that's called mapping. There are other gaps that need filling, but mapping is a good enough term. But then that seems to me very different to forecasting. So the idea of, I think this is a very special kind of problem where you're projecting into the future. And the reason here I put several of these maps out here is because you really want conditional forecasting. So where you can say, if I do this, what would happen or might happen? And if I was to do this, what might happen in the future? So you have this spread of possibilities. And then last but not least, of course, the thing is if you get all of this right, you're in danger of giving decision makers information overload. You know, what if we could model the distribution of every single species on Earth down to 1 meter under 128 different climate and economic scenarios? The human brain can't deal with that. So there's a really important role then for AI to act as an intermediate between people and those data sets to help to boil those data down to a sensible small number of options and identify the pros and cons along with those options so that the ultimate decision makers, who are always humans, usually groups of humans, the ultimate decision makers can make at least the most informed decision they can. I would actually say, incidentally, I reflected on this slightly earlier. I wish I'd put a little robot symbol in on the right-hand side because I think Philip Sadler's talk earlier reminded me that there are cases actually where the things acting and taking decisions may in fact be largely automated or semi-automated systems like drones, etc. So I'll put a robot in, Philip, when I do this next time. Thanks for that talk earlier. And then lastly, just along the bottom here, I wanted to list out some topics that I think come up very naturally in the world of ecology and I'm quite enthusiastic about, and I'll try and highlight them as I go. But the idea of human in the loop, it just comes up again and again and again all the time. Like it's very difficult to fully automate a lot of ecological problems. Maybe, and in fact, it's not even clear that that should be the goal. And instead, we want to make sure that humans are actively involved each step of the way. Foundational models, we had a really good talk on representation learning earlier, and I think there's a spread of these across ecology, geo-foundational models and others, very exciting, lots of room for more and more innovative ways to make use of them. Hybrid simulations, what I mean here is simulating rules-based, it could be physics or other rules-based simulations with scaled up deep learning. And I think there's so many different ways to do that, and it's highly, that's going to be a very exciting area. And last but not least, agentic LLMs. So the LLMs, but not just LLMs, but agentic LLMs. And this is, you know, these are your ChatGPTs and your Geminis and so on. And I'm incredibly excited about these at the moment. I think there's some caution, a large amount of caution around them in the ecology community, however. And so, of course, I'm not saying everyone should go whole hog in on agentic LLMs and do nothing else. But I do feel a little bit we should be investing more. And I wanted to, I hope this won't be, well, if it's a little bit controversial, that's fine. I just wanted to come out here in a sense and just make an argument for these agentic LLMs and why we should do more with them. So for me, I meant to write two, I put 3 key benefits there, sorry. I think there are 2 key benefits to these, broadly speaking. One is that we're now to the point where these agentic LLMs can actually give a much better than random zero-shot answer to almost any question. They're almost always better than random and very often significantly better than random for almost any question, or they can attempt that at any task, usually a lot better than random. And they can be rapidly improved with additional data and feedback in lots of different ways. It's that double recipe that I find incredibly exciting. On the other hand, there are common concerns that come up when I talk to people around these. And again, these are all reasonable, genuine concerns. For example, hallucinations. Biases, evaluations, energy and ethics and so on. And my view on these is that these are all actually nuanced and in practice for a given use case are often solvable. And what are we if not problem solvers? So let's recognize the problems, but then think for particular cases, we can then try and solve them. Well, just to talk about one example, hallucinations. It's a funny thing. I feel like, and I should actually say here and elsewhere, I'm not representing an official view of Google here. This is Drew Purves speaking, because sometimes these areas can be a bit sensitive. So this is my own view on the issue of hallucinations. But you know, what is a hallucination other than just an error? I mean, we usually define a hallucination as it's plausible but wrong. Well, that's the kind of error that all machine learning models make all the time. So if I predict the growth rate of a tree and I think it's 0.12 and it turns out to be 0.18, is that not hallucination? It was plausible, it was 0.12, it was actually 0.18. So I think the reason these hallucinations are popping out to us, though, is because they kind of feel like they're in this new space of facts and human language and so on. So we're not used to seeing so many predictions in that space. So we're not really used to thinking about errors in that space. And so when we're dealing with errors in machine learning, we always think, well, what does it mean for my particular problem? If I'm making an aggregate decision over many things, maybe the errors wash out. I can think about how I evaluate and so on. And so that's an example of how we can sort of recognize the genuine issue, but also lean into it and see if we can solve it. And so my ask really is let's be curious and open-minded about these agentic LLMs. And I would encourage people with their own research groups, encourage that in your students and group members, at least exploration and discussion. And then as a community, I hope we'll increasingly explore agentic LLMs in the mix of what we do. I'm not saying it should be all, but in the mix. But ultimately, of course, do what you want. It's important that people follow their own autonomy. We've always needed that in research. Okay, so there we go. Potential controversies out the way. And then here's a piece of work that I was lucky enough to be involved in a couple of years ago, led by Philip Dorm, where based on this, we thought, well, one simple thing we could do is at least initially just test in a few simple ways the ecological knowledge of the LLMs at the time. This is a couple of years ago now. And this I think it's had quite a bit of impact in the field, this paper actually, because people just weren't really trying these sorts of tasks that seem so outside the norm in a sense of what was possible before. So here's an example where this is just zero shot. You just ask the model, this is Gemini 1.5 Pro, GPT-4, just to draw the range of a species. That's it. You just name the species and say, give me the species range, And we found that, again, much better than random guesses, right? They're not perfect, but they're much better than random. This is zero shot out the box, right? Before any form of few shot or fine tuning or anything, retrieval augmentation, etc. So the fact that they're already back then at this stage showed that you're beginning from a baseline here that's really quite significant, in these models just out of the box. So yeah, it was really a pleasure to be involved in that research. Okay, so back to this structure then. I wanted to step through a little bit in this sort of smorgasbord way and look at some of these 4 categories. One of the reasons I think it's helpful to look at this framework, as I mentioned, is that in ecology, not necessarily in other areas of sustainability research, but in ecology, there's been a lot more work on the left, really, around the data side, and it kind of drops off as you go to the right, like a bit less on mapping, a lot less on forecasting, and a lot less on AI-supported decisions. And that's quite thought-provoking, I think, and might make us reflect on where we think we want to shift and invest in over the coming years to have the most impact. But anyway, let's start. But of course, they're all important, absolutely. And let's start on data. So what the challenge here is interesting, that there's been this enormous increase in the overall volume of public data around ecology. It's increasing rapidly year on year. And this is clearly enough to get us started on all kinds of AI-based modeling. So this is just one of the largest database called GBIF, number of species occurrence records. And you can see how that's changed from 2008 to today. It's an absolutely enormous increase. However, the data is fragmented and gappy. It's fragmented in one sense. Each of the lines on the left there is an ecological database. So it's fragmented in that way, lots of separate databases. And then if you take any one of those, like GBIF, you'll find that they're gappy inside. So they're geographically fragmented and biased. They're taxonomically biased. And they're biased in time, of course, they do tend to be from more recent sources. Although, as we heard earlier, for instance, herbariums would have a different bias. They would go further back in time and start to drop off recently in some cases. And this is actually related to some socioeconomic challenges. I encourage you to read this paper by my colleague Millie Chapman, because often when we look geographically, the biggest data gaps are in less wealthy nations, particularly in the global south. These are areas that typically have more biodiversity, at least as measured in terms of species, that have the greatest current change in things like habitats and therefore the greatest current threat to biodiversity, and where a lot of people are more connected to and reliant on biodiversity for their well-being. So it's a real terrible, ironic shame that the areas of the world where we're lacking the data are the areas where we need the data the most. And so anything we could do in AI to innovate around this, to try to bring more data in from those gaps would be very much something to think about. And again, not just AI, that would be a socio-technical thing. Maybe it'll be startups, maybe it'll be NGOs, maybe it'll be the private sector that addresses that. And then also even at fine scales, like we find data very aggregated around cities and roads when it comes to citizen science data. And if you're a bit naive about that, you would conclude that all species prefer to live in the suburbs. And obviously that's not the case. So you have to be careful to try to de-bias things. So what are some of the methods we can bring there? Well, there's a revolution that's been going on in what we might call passive field monitoring, as we've got these increasingly affordable powerful networked microphones and cameras that we can put out in the field, for example, eDNA and other technologies like drone surveys and of course satellite data and so on. And AI, the AI community has done a great job actually of developing models across these. So we can now do automated ID from these sources. So detect birds from sound, detect species from wildlife cameras, analyze eDNA and so on. So this is an area that's been really great. Another area that's been really great is using that to then incentivize and empower direct human data collection. I'm a big iNaturalist fan. I think it's just an amazing achievement. And this is me using iNaturalist. On the left here, I work outside whenever I can in my garden in the countryside, and I looked down and saw this caterpillar, snapped it on the phone. I was able to ID it as the scarlet tiger moth, right? Now, if we look in the middle, these are the scarlet tiger moth records for the UK, and my garden's in that yellow circle. And that's clearly an information-rich point, right? It's on the edge, and that's because scarlet tiger moth is moving in that direction with climate change, right? So I've picked up that data. Of course, literally within days of me doing that, the data has gone into iNaturalist. It's gone from iNaturalist into the official databases that are used in the UK, right? It's amazing. On the right-hand side, that's me using Merlin in my garden. I'm very proud of the effects of rewilding over the last 10 years. That's a typical 1-minute sort of survey in my garden, a decent collection of species, not all native. You'll notice the pheasant there, but they're still really nice, right? So much to like here, right? And you could almost think, is this just a solved problem then? But it's not a solved problem. There's plenty more to do in the space of AI for data in terms of monitoring. So one of them is that, and this is an example of some of our own work called Perch. This is sort of foundational bioacoustics. So one of the challenges is those bird detectors have only been trained on certain species. The best detectors at the moment go up to something like 1,500 to 2,000 species. There are at least 11,000 species of birds in the world. So even just for the main use of detecting birds, most of the species can't be identified. And of course, they're going to be the rare species that we often care about. So exactly as we heard earlier around representation learning, my colleague Tom Denton and others built Perch, which is a foundational bioacoustic model. And they've shown then that with the right model, you can encode the sound into an embedding and enable few-shot learning in the field. And so that means that field biologists can now very quickly develop detectors for new species. But of course, also, these representations have other uses. So you could also, it doesn't have to be a bird species. It might be a specific call you're interested in, like an alarm call or distinguishing juvenile from adult birds. Or, for example, search. Search is really important because if you have huge amounts of audio and you pick up 1 or 2 bird calls, you might want to use that as a key to retrieve similar recordings where that data might also be present, and so on. So it has many uses. And it's just amazing that on the right here, we can see that you can, with just four recordings of a bird, you can get a 0.95 AUC ROC. It's just insane, right? I mean, just unimaginable previously. So, and also one key point I want to mention here is that, of course, there were audio embeddings before Perch, but these were general purpose embeddings based on sounds from things like YouTube. And interestingly, they basically didn't work for this purpose. And that's because those sounds are actually something like 75% human voice, the rest of it 75% music, right? And it turns out that the signatures of those things don't create representations that are good for understanding natural sound. On the other hand, Perch, trained purely on birds, turned out to transfer really well underground for detection of fish. Mind-blowing, and it suggests that there's something about the way that animal communication has evolved that is actually in common between the land and the ocean that meant that transfer learning task worked. No fine-tuning involved. This is pure few-shot learning for whales, other species, and fish. Amazing story. And then more recently, what they've done is actually created an explicit agile modeling framework where researchers can have their sound recordings and they're able to use the search to retrieve other similar recordings, and they build their own few-shot case. And they've actually shown in this work that genuine field biologists that hadn't used bioacoustics in this way previously could develop a detector for a new species in a total of 1 hour of human effort. I mean, I'm going to do this a lot in this talk because this whole thing is blowing my mind. I've been around for a long time as an ecologist, right? But 1 hour, it's just completely bizarre. Amazing. Okay. And then another piece of work in a similar vein I wanted to highlight here is a recent paper from Sarah Beery and colleagues, Edward Vendro, Sarah Beery and colleagues. And they're using embedding-based retrieval of images. So what they're doing here is they're taking the iNaturalist images. So those images, which are amazing, right? They're labeled GPS coordinated images and they're labeled with species. That's fantastic, but it's also an image. And what they're using then is embeddings to retrieve other information from those images, a little bit like we saw in the herbarium specimen earlier. And again, with human in the loop. So now you can start with a natural language question initially. They use a language model to then embed that with the VLM space. So you can say, in this case, what is the approximate spatial range used by California condor 26? And you can go through and you can find the records of the condor in this example, and you can go back then verify those with human in the loop and eventually create this, which is the points on here. So this particular bird just happens to have been picked up a number of times, you see. This is a favorite example in the paper. So this is then, they're pulling out certain species, but then they're pulling out which other species they're associated with or what they're eating. The reason I really love this is that we've always been incredibly short on interaction data in ecology, things eating other things or otherwise interacting with other things. So, historically, we were massively short of all data. Nowadays, we do have quite a lot of species occurrence data, but we have very little data about interaction. That's kind of ironic because ecology is literally the science of interactions, right? So, and the actual core thing we're usually missing. And now this gives us the possibility for pulling out those from unstructured images, which is just incredible, I think. There's another example, though. There's a lot of data. It's not all about field monitoring. There's a lot of data that's locked away in the literature. And this is a recent piece of work that I think is incredibly impressive, which is going through, again, using natural language processing, I think LLMs, to go through, trawl huge numbers of papers and pull out species interactions. And then they're drawing that as a graph here, things like competition, predation, and things like this. So it's just incredible, again, like being able to pull this volume of data from the literature in that way. And here's yet another one, which I'm very excited about. This is a slightly different take on this problem. So I mentioned the fragmented ecological databases we have. And people's usual response to this is to say, we all need to work as a community together to agree standards and create an open database. And of course, I would love us to do that, right? But I've also been hearing that for 25 years as an ecologist. And I think sometimes people do that and it depends on culture. But in many areas of ecology, we haven't done it. Suddenly, so what's happening, by the way, maybe I should explain this, is the use of LLMs. So you get an LLM to read and inspect the databases, a multiple set of databases, and then to come up with a way to bring those all into the same schema for you. So now I'm suddenly thinking, if this really worked, we don't need to agree common standard. We don't need to join our data. Let's just let the LLMs do it, right? Like let them go that hideously difficult work. That's why we're not doing it really, because it's such hard work, right? Or maybe we get the LLMs to do the hard work and bring that all together. So maybe all of those databases could be harmonized in the near future. I mentioned earlier on the panel about, baseline, that might sound crazy, but everything we're doing now is crazy compared to 10 years ago, right? We're in a totally different world. So why not? Maybe in 5 or 10 years, we won't even think about the fragmentation of ecological databases. It will just be something in the background and the LLMs will just be harmonizing it all for us. Maybe. Really fantastically pioneering work. And this is some work I was lucky enough to be involved in over the last couple of years, which is when you're mining data from the literature, one of the key things we always care about in environmental sciences in general, and in nature in particular, is georeferencing. We want to know not just what's in the paper, but where was the study carried out. And usually, unfortunately, over the years, we didn't keep that metadata with the papers. So as a human, you can often read a paper and with enough effort, basically put that study on the map. Well, we created a benchmark testing if LLMs could do this. And we showed that they were quite good at it. If you just give them a map, they're pretty good at putting a little picture of a map. They're pretty good at putting that map on the real Earth. And if you have a document to go with it, which you usually do, they're very, very good at it. And we've carried on working on this since. And we're now at the point where it's pretty much solved. So if you've got a map or you've got a document with a map in it, we can basically accurately georeference that. And then along with it, georeference all the data in that paper, right? It's kind of amazing. I'm very excited about that work. Okay, I'm going to go to mapping. Now, we heard quite a lot about mapping, actually. I won't say too much about this. I did want to say this is a big focus of our work at the moment. So we've been working on mapping forests. Forests are a big topic today. So we've heard about mapping forests and mapping change in forests. This is some work that my colleague Maxime led, creating the best yet fine-grained map of natural as opposed to planted forests, which is very important in a lot of policy settings. And we've also open sourced all of the models and the code bases and the data behind that as well. Similarly, we've gone a level deeper than that and looked backwards from 2000 to map the underlying driver of forest loss, for example. So what you're seeing here is not a label of the current state, but a label of the cause of forest loss in those places. So here in Scandinavia, that's mostly logging, but in other areas of the world, that can be shifting agriculture or conversion to permanent agriculture, etc. But I know we heard a lot this morning from Philip around many other exciting use cases of mapping forests as well as mapping change. One area we have been thinking about here is when you talk to practitioners, they often ask about the uncertainty on maps. And we mentioned hallucinations earlier, and I think we all now know that you shouldn't just naively trust the output of an LLM, right? You should think about hallucinations. But the funny thing is, when it comes to producing segmentation maps of the Earth's surface, there's been a surprisingly small amount of explicit research on the uncertainty side of it. So this is some work from my colleague Melanie, who's actually explicitly testing if you take your segmentation maps and you look pixel by pixel at the entropy, does that entropy actually predict which pixels may be right or wrong? And surprisingly, it turns out it doesn't really. So entropy seems like a perfectly sensible measure of uncertainty, but it's not strongly correlated with the actual errors. It is at a tile level. So if you take a larger tile, if on average the whole tile has a high entropy, that is correlated with the whole tile having a lot of mispredictions, but it's not true on a pixel by pixel basis. And then in the paper, we have some suggestions for some other methods that can address that. But the main conclusion of the paper actually is to explicitly build this into workflows. So as well as having a train test data split, is actually doing another split, which is explicitly reserved for testing your uncertainty model. Because without that, then it's hard to know whether we're really providing the right measure of uncertainty to downstream users. Another innovation that Melanie has here is actually a sampling methodology. So that you're not just presenting a map of uncertainty, but you're creating a set of plausible outputs. And that's done in a way that's spatially coherent. So it's not just white noise. So you're seeing each of these is basically an equally plausible output of the model, if you see what I mean. Apparently, the previous work there was mostly done in medical imagery, things like segmenting from X-ray images. Oh, sorry. That's kind of groovy, right? Was that my fault? Did I hit something?
No,
oh. It's tempting to use it as like a sort of theatrical. Anyway, very, very good. Thanks. And so I just wanted to say, so, okay, but coming back from mapping a little bit, and I think people are probably aware of this, there's a whole session on this tomorrow, a workshop on this tomorrow, is just to give a nod here to the rise of geo-foundational models. So again, this is representation learning like we saw before. And what these models are doing is they're different methods that you can use, but they're distilling down a very high volume, complex satellite and other geodata sets into vector representation vectors per pixel. And the idea being that, as we saw earlier, then as a downstream user, you can just use, even things like k-nearest neighbor or linear methods against those pixels. So this is a big trend. And the idea here is that up to now, the kind of remote sensing that you just saw has been a very specialist activity. Need a lot of specialist skills and a huge amount of compute. Now, if you can pre-compute these embeddings, then actually downstream users, a much wider group of downstream users can do this kind of remote sensing like for themselves, if you like. It's very exciting. And I just want to highlight a couple of those. One from my colleagues at Google. This is Alpha Earth Foundations. And then a complementary one, I think, from colleagues at Cambridge. Sadiq, I know you're here, and probably some others that contributed as well, called Tessera. And they've got some similarities and differences, but I'd encourage you to look into this area because I think we are in an era now where this kind of remote sensing could become very democratized so that, a much wider group of people could be building their own custom maps for a much wider group of downstream metrics very easily. So it's quite an exciting time, actually. But of course, also when we're onto mapping, though, not all mapping is remote sensing. Remote sensing really works where you think that the thing you're modeling leaves a significant signature in the satellite data or aerial data. So a great example actually on tree species distribution modeling this morning, and that obviously makes sense. And trees in Sweden are going to leave a very significant signature. So that's a remote sensing problem. But, when we think about species distribution modeling in general, we think about insects, worms, fungi, birds. It's not reasonable to think that many of these leave an explicit signature. And so there's a whole area here that's called species distribution modeling. That's been around for a while, but now we're seeing deep learning methods move into those. And one of those that I think is fantastic came out a couple of years ago, Cole et al., the spatially implicit neural representations. So they actually showed how you could co-embed as a joint problem, an entire assemblage of species. And so you end up with a joint embedding of space, so latitude, longitude, and all of the species together. It's absolutely fantastic work, really, in two ways. So one, it was very innovative to treat, traditionally in ecology, we've treated each species separately, despite the fact that we know that ecology is so interactive. In doing joint modeling this way at scale, using deep learning, it was really exciting. The other one is they built a partnership with iNaturalist. So very, very quickly after the paper came out, iNaturalist now runs Sinner. They refresh the model every few weeks or something. And now they can provide distributions like this back to users. And so as a user, that scarlet tiger moth observation of mine is already reflected in the iNat Geo model for that species by now, right? It's just what an amazing, amazing thing. Having said that, of course, there are plenty of issues at the moment with these models that follow from the biases in the data. We've actually been working at this. So we've taken a model that's similar in spirit, but it's actually a graph neural net model. And we made a couple of additions. On the one hand, we're bringing in those geo-foundational models. So I should say for those that are interested, it's a heterogeneous graph neural net with two kinds of nodes, species and location nodes. And then we bring in the geo-foundational models, alpha Earth foundations in our case, on the location nodes. And we bring species traits in on the species nodes, things like lifespan and body mass, or for plants, wood density, things like this. So the idea is it's kind of multimodal joint modeling. And this is just some recent results. We just released our first results. And this is showing, I think, platypus and a couple of other species in Australia. But we're just not used, as ecologists, we're not used to seeing distributions with this fine-grained structure. And what we're seeing is strong evidence, actually, that we think we can actually debias. We can naturally somewhat debias from the biased citizen science data here. So we're just training against GBIF. So I'm sorry I can't talk about more of that at length. I'm very excited about the work, but I better get on. And the only thing I did want to point out a paper here, though. So this is CINNER-SAT. So this is a paper which has taken CINNER but added the geo-foundational model as inputs, so which is something in common with ours, and done that for 5,000 species in Europe, plant species. So fantastic work. So please do check that work out as well. And another exciting thing we can do with mapping species is actually to bring language in different ways, including LLMs. I just want to give a quick nod to that on the left, a fantastic piece of work here where you're able to bring in, you're able to use a language as an additional input into the species distribution model. That can be the taxonomy of the species or other forms of language. And this is a personal experiment on the right here. This is the first time I've shown this in public. It's purely just me doing this as a side project, but this is a pure LLM SDM. It's a prediction for European fig, and it's a system where you just put the species name in, and out the other end comes a species range. And that's it, no data, nothing. And it was kind of partly as a sort of thought-provoking experiment. The thing that surprised me about it is whenever I've mentioned it to people, no one's ever guessed how I did it. It's kind of funny because I thought there was kind of an obvious way to do it. So I'm going to leave that as a little puzzle. And if anyone wants to talk to me about it, or indeed if there is actually anyone that wants to seriously study this to say how accurate is it or not, then I would actually, if you want to do that and you've got some time to do that, then I'd be very happy to talk to you more seriously, by the way. And maybe I should say, if this has a utility, and I think that's a big if, I think of it as being something that can create priors, because in a sense, that's a very appropriate use of, it seems to me, of an LLM, in the sense that if they're working properly, they kind of are boiling down, global belief about something, right? So I've got at least one nod. Thank you. It's very nice to see that. So, so like all priors, you then want to improve it and adapt it with actual data and evaluate the result and so on. But anywho, language and species modeling, very exciting. So I better, I've got only 7 minutes until I get to the 40 mark. So I just want to say a little bit about these other two. So forecasting, again, there's a lot less work here. It's much harder because forecasting is harder anyway, but forecasting things in ecology is very complex, and often the relevant timescales are quite long. So, if you think about something like weather, you've got repeated signals every day and at least every year to kind of test to constrain your forecasting models. Often we're thinking about things like forests or the effects of climate change on species, which are slower. So these are kind of non-linear, complex, but annoyingly slow processes. So we don't have repeat cycles to train on. So it's a very difficult challenge. One bit of work we've done recently is, and this is an example of forecasting where we're forecasting deforestation risk. So we're taking observed deforestation events and building a pure satellite model that predicts those a year ahead. This is a very interesting vision problem and remote sensing problem, but it's also, we hope, like it's something that is really needed in the policy community and in the private sector to do things like clean up supply chains. So really proud that we've been able to do this. And we've been able to show that this pure satellite approach is as good or better than approaches that assemble specialist features together. But because it's satellite, that means we can do it consistently globally, just like we heard actually with EchoSat earlier. They use that language, consistent global, exactly, that's what you get out of this approach. But of course, that's a very near-term example of forecasting where it kind of is a sophisticated form of trend projection. And that makes sense when you're looking at short time scales. But would you want to do that to project the potential impact of climate change on Danish forests for the next 50 years? Probably not. You want to do a different approach. So what can we do there? How can we tackle non-linearities? I wanted to share a thought here, and this is this area of hybrid simulation AI. And I think this is not ecology. These are from my colleagues that built GraphCast, and it's an amazing project from my colleagues at Google DeepMind that's really triggered a big change in the weather forecasting community. So this is a pure deep learning weather forecasting model that actually outcompetes previous models. And not only that, but it can run on a laptop, whereas the previous models ran on supercomputers. An incredible thing. But how that's actually done is, on one level, looks quite simple in the sense that you have input data. So you have the weather state, and then you have the next state, and you just train a model. I mean, it was a difficult thing to do. You just train a model that predicts the next state from the existing state, and it has a sophisticated graph neural net to do that. But the reason I mention that here is that where do you get this state from? Because the state is actually a completed grid of information. So what you've actually got in reality is weather stations. So that grid of information is what's called reanalysis. So it's actually the output of a physics-based model. So what you've actually got is over here, you've got weather station data. Those weather station data are being fed into a traditional physics-based model, which is filling all the gaps based on that data. That's then being stored as data, the output of that. And then we're training a deep learning model against that. And what that means then is that in that data, you've got two things. You've got the signature of all the physics, but you've also got all of the nudges that are coming from the real data, and that whole signature's there. And so that's why that thing in the end can outcompete the physics-based model, because it's got all the physics if it works, but it's also got all the other stuff that the physics model never captured in the first place. It's sort of in the data-driven stuff. So I mentioned this because I think this is one of many different ways to hybridize sort of rules-based models, in this case for physics, with the power of scaled-up deep learning. And I think there are so many potential ways to apply that in ecology as well. So really, wherever we've got dynamic data, and/or we've got models that forecasting models which we think have value. They don't have to be perfect, right? But they just have to be values. And I think there are plenty of those in ecology. Population dynamics models, fisheries models, models of tree growth and mortality and forest development and so on, physiological models, even some animal movement models and so on. So imagine taking all of those and doing something in this hybrid AI space. Maybe it could be as transformative for ecology as GraphCast has been for weather. Here's another take on forecasting, though, and this is one of my favorite papers actually from the last year or two. It's not in the space of ecology; it's in epidemiology. I think the team that built this, I'm in danger of them thinking I'm like a stalker because I just keep emailing them all the time and just saying, I just want to say again how amazing this paper was, and I put it into this report, and I put it into this talk, and so maybe I'll stop doing that. But so what I love about this is it's doing something. It's another case then, and again in a thought-provoking, really fascinating way. It's another case of using LLMs. But I think there's a tendency, and I'm exactly like this too, at the moment, to mostly use LLMs in a kind of surgical, like kind of bolt-on method, right? We use them to get some data on the one hand, or of course things like coding, obviously, or even at the other end, there's loads of ways you can use LLMs for evaluation. I didn't mention that, but I think that's a really exciting use of these. But what Pandemic LLM is doing is predicting COVID admissions to hospitals, but it's using the LLM as the core prediction engine. So you assemble different data together that you think are relevant to that problem, and it can include news stories, tabular data about previous previous hospital admissions. You could put anything in there, right? And you form basically a long prompt, and then you say to the LLM, okay, now give me your prediction for the next 10 or 20 years. I mean, it's kind of, you can imagine next 10 or 20 weeks. And you can imagine that this is a really unorthodox approach, right? That might freak out a lot of people, but that's what I like about it. It's really kind of, I think it's quite a pioneering, quite challenging, thought-provoking thing to do. And of course, they show in the paper this beats traditional methods, and it's not hard to understand why it would for hospital admissions. You could feed it school holidays, you could feed it news stories, right? Like these LLMs can absorb any kind of information. So I think that's very thought-provoking about whether there could be some cases in ecology where we could do something similar to this as well. Because the thing is, this happens anyway. It's just that the thing doing that judgment is a human today. What actually happens is we have these forecasting models and they make a certain prediction. And then when it comes to making a decision, an expert will then combine that with their own understanding of the problem. So do you know what? They're going to, if they've heard a recent news story, so this is kind of potentially formalizing and then scaling that approach. I think it's so exciting. Right, I'm at the 40 mark now, and I very much am nearly done because I'm on to decisions. And this is the area where there's been by far the least work, I think, to date in terms of AI for ecology. And it's understandable because decisions are really messy. As I said, you've got to deal with information gaps combined with information overload. And you have to deal with people. Like, the people making the decisions, and the people making those decisions, it's never about one thing either. Up to now, you might have thought, I'm an ecologist, and the minute you come to make a real decision, power networks matter, rivers matter, people matter, local regulation and law matters, economics and finances matter, and so on. So it's a difficult space, but so I think there's so much we could potentially do here, a lot more we could do with AI. We heard a good example actually earlier from Philippe around using cost optimization is one. I've not covered that here. I just want to highlight a couple of things that have excited me recently. So one is by Sadiq, who's here at the workshop. Hello, Sadiq. Thanks for the wave. And so this is connected to a previous, ongoing project at Cambridge, a long-standing project called Conservation Evidence. And this was a human process driven by Bill Sutherland and his team, who for many years have been assembling cases where people have tried interventions in the real world that affect nature in some way, like digging a pond or mowing a lawn, this kind of thing, a wide range of these. And they very carefully put all of those together. They find all the papers, and then they boil those down to summary reports that allow people to have evidence and advice for what they do. And what's exciting about this paper is that they've used LLMs then to automate the first half of that problem, to actually discover all of these reports, to make sure that they're high quality and that they match, and to get all the metadata that would traditionally be done through human labeling, to get all of that together. And they've shown that the performance of the system is as good, I think roughly as good, or maybe even better, or maybe almost as good. I'm trying to read Sadiq's eyebrows from near the back, but anyway, but it's very good. And so now this offers the opportunity for scaling up this approach, which is really fantastic. Now, of course, then I'm going to assume that work is going to feed into the rest of the conservation evidence work, which means that we can expect then to see a lot more grounded advice coming out of the project as a result, simply as a result of lots more data going in, but potentially, because I'm imagining that they might be considering applying LLM similarly to this part of the problem, creating the similar reports to the evidence. So I'm just sort of guessing that they're likely to be making that link as well. So that just seems potentially very, very exciting. Of course, it's kind of sidestepping a lot of what we talked about. This is kind of purely just reaching into the ecological data, summarizing it all together to make advice. I think there could be other cases, though, where actually you've got something like an LLM sitting on top of all of that geodata. And there's an example here that I really like from WRI, which is called Global Nature Watch. And this is an example then, they're surfacing all of these geo layers to the LLM that allows natural language queries on top of that. And the last thing I wanted to show is, of course, let's not forget that this stuff is running on people's phones now. And so this is a little future-facing thing, thinking, can we imagine one day that everything I talked about, really, the AI for data, AI for modeling, AI for forecasting, AI for decision-making is all being packaged up such that any individual anywhere can get the very best knowledge and advice affecting every decision that they take that affects nature. And when I think about that, I feel excitement and joy, and I'm done. Thank you. Thanks all.